for being late, but yeah, we'll start almost on time, and Anindya will tell us about deterministic approximation counting for Juntas of Degree-2 PTFs. Subhash?
Can I start now?
Yes.
Okay. So
I have a question.
Yeah.
Why do you say Juntas of Degree-2 PTF instead of just functions of Degree-2 PTF?
Because the dependence on the number of functions is going to be triply exponential.
So.
Maybe the Juntas will make it disappear. I don't know. Okay, so we saw a lot of LTF PTF action in the last talk itself, but I'm still going to recap the definition in one slide. So the object of interest in this talk, the degree D PTFs. So that's nothing but a Boolean function of the form sine of a polynomial, where the polynomial is of degree D. So f equals sine of p, where degree of p is d. Here the domain is defined to be -1, 1 to the n, so the hypercube, but you can take the domain to be r to the n and equip with any measure. And in this talk, we are just going to focus on the case when d equals 2. Okay, so cutting to the chase, the problem we're interested in is the following. You are given k degree-2 PTFs, f1 to fk over the Boolean hypercube, and a function g, a Boolean function g on the k-dimensional hypercube, and you want to deterministically compute the quantity that if you choose a random point from the n-dimensional hypercube, what's the probability that g of f1 to fk evaluates to 1. So this is a Junta of degree-2 PTFs because we are thinking of g as having arity k, which is constant. So that's why we are calling it a Junta, answering Adam's question. And we don't want to estimate we don't want to compute this quantity exactly because it's sharply hard to compute. So we will be happy with deterministic, we will be happy with additive approximations. So we just want to compute this probability up to an additive epsilon. Rocco already did some survey of this kind of stuff in his last talk, but let me just quickly go over the motivation. Okay, so sorry. Another important thing is that we would like the running time to be some fixed polynomial in n times some function of k and epsilon. In particular, another way to rephrase this thing is that we would like the running time to remain polynomial in n for even k's which are slightly superconstant and epsilon which is slightly subconstant. On the other hand, if the running time was n raised to k or something like that, then for any superconstant k, the running time will not be polynomial. So motivation, Rocco covered a lot of motivation for this kind of deterministic counting in the last talk. So that's the first bullet. But really, any interesting class of problems has the property that the counting version is sharply hard. And say DNF counting or counting for half spaces. And in fact, and this is what motivates the study of approximate counting in the first place.
So the word self-respecting, it has a formal meaning?
No, it was just intended as a joke. It was just intended as a joke. Right. And formal meanings associated there. Okay. And neither does the adjective really have any formal meaning. But okay, for Boolean functions, from the perspective of Boolean functions, in fact, even the decision versions of the problem, just deciding whether there is one satisfying assignment versus no satisfying assignment, most of these classes will have the property that even this decision problem will be NP hard. And hence, you cannot even hope to get multiplicative approximation guarantees for the counting problem in polynomial time. So the only reasonable problem left in the landscape of approximate counting problems is that, okay, so the only thing you can now hope to do is get additive approximations to the counting problem. Okay. And as Rocco again mentioned in the last talk, there's a simple, trivial, random sampling based algorithm which, given any efficiently computable function, can get a additive epsilon accurate estimate of the fraction of satisfying assignments. Just random sampling works. So, okay. So the only interesting problem left is that we would like to deterministically approximate the fraction of satisfying assignments for a given class of Boolean functions. This is the only interesting problem left.
It must also be possible for all instances
Yeah, and so So you can consider two classes of problems here. One is that you give the algorithm will actually look at the given function, or there is some sort of an oblivious algorithm like a pseudo-random generator. So we are considering the weaker problem here, where the algorithm will actually look at the problem, will look at the given instance, and then do the approximate counting. Okay, so this was all motivation, but there's another motivation really for this thing. It's known that if we can prove really strong circuit lower bounds, that implies that every efficient randomized algorithm can be de-randomized, and proving the hypothesis is really out of question at the moment. So we should do the next best thing, prove the consequence. So we should try to consider specific classes of functions and see if we can, specific classes of randomized algorithms, and see if they can be de-randomized, at least if we can prove some of the consequences. And that is what gives rise to the field of de-randomization, that we try to consider specific classes of functions and try to see if the randomized algorithms for counting can be de-randomized. I guess I don't need to motivate anymore. So anyway, approximate counting of PTFs, small survey of the field. So again, Rocco mentioned in the last talk that the landscape of counting for half spaces or linear threshold functions looks really nice right now, the state of results. Stefankovich, Vimpala, Vigoda, and Gopalan, Clivens-Mecca both independently and concurrently gave deterministic algorithms in running in time poly n 1 over epsilon, which can count the fraction of satisfying assignments for half space over the uniform distribution on the hypercube. So I'm always talking about the uniform distribution on the hypercube, up to a 1 plus minus epsilon multiplicative error. Of course, if you consider any virtual classes of functions like degree 2 high or higher PTFs, you cannot hope to get multiplicative guarantee. And the last talk has the state of the art in this particular problem, that if you're given a degree 2 PTF, then you can compute you can estimate fraction of satisfying assignments to an additive error epsilon in time poly n times 2 to the poly 1 over epsilon. That was the last talk. And now you can ask, what about virtual classes of functions coming from these LTFs and PTFs of degree 2? So for that, for k Juntas of half spaces, so if you consider a function of k half spaces, Gopalan, O'Donnell, Wu, and Zuckerman, they gave a deterministic counting algorithm for this class running in time n to the k plus log k over epsilon for an epsilon additive error. And in fact, if epsilon is really small, epsilon is somewhat large, like it's super inverse polylogarithmic, I don't know how to say this quantity, then they actually get a running time which is exponential in k times poly n. In fact, they accomplish something much more. They give pseudo-random generators, but we're not discussing that. What about functions of PTFs? So Juntas of half spaces, the interesting results. What about functions of PTFs? So again, there's in the past, so the only previous result relevant to us is that Dyko, Nicholas, Kane, and Nelson showed that k Juntas of degree 2 PTFs over the normal distribution, over the n-dimensional normal distribution, can be counted up to an additive epsilon in time n to the k times poly 1 over epsilon. And they achieve a similar running time with a worse dependence on the k when the distribution is replaced by the uniform on the hypercube. Okay, so those are so in particular, the running time for any super constant k or sub constant epsilon becomes super polynomial in n. So this. And this is now this is the problem we are interested in. We want to do the same task with a running time which remains poly in n for some super constant k and sub constant epsilon. So we want to achieve a running time, for this problem which is poly n times some fixed function of k and epsilon. Okay, so now this is the main theorem, that there is an algorithm which runs in deterministic time poly n times some function of k and epsilon. This function of k and epsilon is rather bad. It's like triply exponential in k and doubly exponential in epsilon, but it's still some function of k and epsilon, which given any function g over the Boolean hypercube, with Boolean function over the Boolean hypercube in k dimensions and k degree 2 PTFs, outputs the number nu, which is an epsilon accurate estimate of the probability that when you take the random point on the hypercube, then g of f1 to fk evaluates to 1. Okay, so is the result clear? The main result? This is not a pseudo-random generator. The algorithm will actually extensively look at the instance. And for this talk, because you can just assume G to be an AND, because any function over the k-dimensional hypercube can be written as 2 to the k different ANDs, and we are really paying something much more than 2 to the k. So just think of G as AND. Okay, and proving this main result, similar to the last talk, almost all the work goes into proving the same result when the distribution, when the input distribution is changed from the uniform distribution, the hypercube, to the n-dimensional normal distribution. So most of the work goes towards getting the same algorithm when the domain is equipped with the standard normal measure rather than the uniform measure, and then you use invariance principles and stuff to go from normal to the Boolean thing. Okay. So as I said, technique for proving the main result is first you prove the main result over the normal distribution, and then following the previous talk we can, so there's all this awesome work by Elkanan, Shistov, Ryan, who give these invariance principles, which shows that once you can do the counting over the normal distribution, you can achieve the same approximation guarantees. You can do the same counting algorithm for the degree 2 polynomials, for polynomials over the hypercube as well, over the uniform distribution, the hypercube as well, provided these polynomials are regular, meaning that every variable has very small influence on each of the polynomials. So this is pretty standard. And so what you now need to do is to show that what if some of the polynomials are not regular. So then you want to decompose it to a case. So give, sorry.
You should need more than each polynomial.
Why?
Presumably you can run into problems with like the difference in two of them is highly irregular.
I don't think that comes up. Okay. But anyway, the important thing is that, okay, so next we prove a new regularity lemma. I'm not going to discuss the regularity lemma because it kind of follows very standard techniques. But basically we show that if you are given k degree 2 PTFs, k degree 2 polynomial threshold functions, you can construct a decision tree of depth depending just on k and epsilon, so c, k and epsilon, such that with high probability over the leaves of the decision tree, the following will hold. That if you restrict all the variables along the path leading from the root, going from the root to the leaf, all the resulting degree 2 PTFs will become regular. Okay, and so equipped with this decision, and this decision tree can be constructed in time, which is poly n times 2 to the ck epsilon. So this is efficiently constructible, and that will mean that, okay, once you know how to count for regular PTFs, you can just go over all the possible paths of the decision tree, do this counting at every leaf, and you can get an estimate. I don't want to go over this thing too much. It follows kind of existing results in the field. The proof techniques follow from existing results in the field. Okay, so what it boils down to is proving this main technical result over the normal distribution. On that, if you're given k degree 2 PTS with the domain equipped with the normal distribution, then you want to do this additive, then you want to do this approximate counting. And the roadmap towards achieving this is, first we'll state a new central limit theorem, then we'll show how the central limit theorem is helpful to do the approximate counting when some nice conditions are met on the polynomial. The nice conditions will be similar to what was used in the previous talk, and then we'll show, okay, that a general case can be decomposed to meet these nice conditions. So you can take the general, given k degree 2 polynomials, you can do some restriction, something to meet the hypothesis of the CLT. So what I'll do is I'll state the new CLT, then go over how it's applied, and finally come to the proof of the CLT. Okay, so basically we'll prove a new CLT for the joint distribution of k degree 2 polynomials which all have small eigenvalues. What do I mean by eigenvalue of a polynomial? So we call that any degree 2 polynomial px, I can always write it down in this form, x transpose ax plus bx plus c, where b is a vector and a is a matrix, symmetric matrix. And the eigenvalue of a degree 2 polynomial is just defined, the maximum eigenvalue of a degree 2 polynomial is just defined to be the maximum singular value of the matrix A. I'm going to show that if I have given a collection of k degree 2 polynomials, all of whose largest eigenvalues are very tiny, then their joint distribution looks like a normal in certain metric. Sorry? Tiny compared to the variance. Tiny compared to the variances. Yeah, so this is, yeah.
Wait, if you want the joint distribution to be Gaussian, presumably you want linear combinations of them to also have. I guess that's probably implied.
That's probably implied, yeah. I'm not saying what metric. I mean, this is something weaker. We'll show it in the Kolmogorov distance, in the k-dimensional Kolmogorov distance, which is what we require. Okay, so this is the main theorem. This is the new central limit theorem. That if you have k degree 2 polynomials over the normal distribution, and all of them satisfy three conditions. So they satisfy three conditions. The eigenvalues of the maximum eigenvalues of each of the polynomials is bounded by epsilon. The variance is always bounded by 1, and at least one of the variances is at least c. Okay? Then the joint distribution looks like a multidimensional normal. And what multidimensional normal can it look like, if it at all looks like a normal? Well, the one which has the same first and second moments as the joint distribution. So that's what this thing says. It says that then the joint distribution of the polynomials p1 to pk looks like a multidimensional normal with the same mean and covariance matrix as the p1 to pk, and the distance, the Kolmogorov distance between these two distributions is k to the 2/3 times epsilon to the 1/6 divided by c to the 1/6. So if all the polynomials had variance 1, suppose consider a simple case when all the polynomials had variance 1, then the Kolmogorov distance is just k to the 2/3 times epsilon to the 1/6. So it's saying.
What's the Kolmogorov distance?
I'm going to define the Kolmogorov distance in k dimensions as the obvious analog of the distance in one dimension.
Anindya, this isn't like obvious or easy or anything if k is 1, right?
This is obvious if k equals 1.
Oh, it is?
Last talk showed that. Basically, you can, if there's only one degree to polynomial, then you can do a basis change and then it looks like a decoupled thing. You can apply the Bayesian kind of thing. Okay, so k equals 1 follows by Bayesian. And okay, what's the k-dimensional Kolmogorov distance? It's just this, that you take a soup over theta 1 to theta k, which are real numbers, and then you ask what is the difference between the probabilities that all zi's are bounded by theta i's vis-a-vis all the z prime i's are bounded by theta i's. So if you take k equals 1, you're just asking what is the probability that difference of the probabilities that z1 lies in one side of the real line versus z prime 1 lies in one side of the theta line. There's an obvious extension. Okay, so the central limit theorem makes sense? Okay, why is this CLT helpful? Why do we care to have this CLT? So applying the CLT. So if you are given k degree 2 PTFs over with the normal distribution as the domain. So now from now onwards the domain measure is always the normal distribution. And Fi equals sine of Pi, where of course you can assume that the variance of Pi's are all 1. You can just rescale the polynomials. So you can always assume the variance of the Pi's are 1. And you assume an additional condition that the maximum eigenvalues of all these Pi's is bounded by epsilon. Okay. Now put G equals and. If G function, the junta was and which we said is the most general thing you can anyway do, then all you need to compute is the probability that all these Fi's are 1, which is equivalent to the probability that all these Pi's are greater than or equal to 0. However, the probability that all these Pi's are greater than or equal to 0 by the CLT is very close to the probability that a multidimensional normal, all the coordinates of a multidimensional normal are greater than or equal to 0, where the multidimensional normal has the same first and second moments as P1 to Pk. So given P1 to Pk, you can explicitly compute what this multidimensional normal is. So if you are shooting for approximate counting, it suffices to compute the right hand side. But the right hand side has no n. It has reduced to a finite dimensional problem. There is only their k square parameters. There are k first moments and there are k square second moments. You just want to compute what is the probability this multidimensional normal is always all coordinates are greater than or equal to 0, lying the positive ascent. This can be computed in time k to the k, but doesn't matter. It can be computed in something depending just on k. And So we are done in this case. So if you work out the parameters from the CLT, if all the eigenvalues of the polynomial are small enough, we are done. So this is why the CLT is helpful. So all we should now try to do is, how am I doing on time?
20 minutes.
Okay. So if all the eigenvalues are small enough, then we are in good shape. So now what we should do is to try to do some procedure by which we can bring the polynomials to have small eigenvalues. So what happens if some of the polynomials have large eigenvalues? So we'll consider a toy case of what we'll do. So assume that all the polynomials are diagonalizable in the same basis. Okay? Diagonalizable in the same basis means that, see, all the PIs, okay. So all the PIs can be, so PI can be written as X transpose AIX plus BI times X plus C. If all the matrices AI are diagonalizable in the same basis, then we will consider this toy case. And then it means if they are diagonalizable in the same basis, then you can write Pi as summation alpha ij Ljx square plus beta ij Ljx plus Ci. Okay, where Ljx's are the linear forms which diagonalize the matrix AI. And they're all diagonalizable in the same basis. And because of the great property that the Gaussians are invariant under orthonormal transformations, the joint distribution of P1 to Pk, which is what we are interested in, remains the same if I just rename the variables from Li to call it Yi. So these are just new independent normals. You can just call them that. And so now these are the polynomials we're interested in. So this is the joint distribution we're interested in understanding. And so now there are two conditions. So if earlier, if all the eigenvalues are small, the maximum eigenvalues of all the PIs are small, that translates to just saying that all these alpha ij's are all small. So then we already know we are done. If not, then following an analysis in this paper by Parikshit, Ryan, E and David, it can be shown that there is some sort of a decomposition you can do. That there is a small set of variables of size k over epsilon square such that for any pi, at least one of the following is true. Either it will happen that with high probability if you restrict all the variables in L, then the sign of pi is close to a constant, meaning that essentially this pi just depends on the variables in L. Or if you restrict the variables in L, then the eigenvalue of the resulting polynomial becomes small compared to its variance, in which case you can roughly apply the CLT. So either a polynomial is just dependent on the small set of variables, or after you restrict the values, the resulting polynomial has a small eigenvalue compared to its variance. So either you can apply the CLT or it has become a constant, so you can become close to a constant, so just replace it by a constant. Okay, I'm not being super clear here, but this is a hazy idea. And this is all in the toy case though, when all of them are diagonalizable in the same basis. So if you can do this, okay, so now there's a win-win analysis. So first restrict all the variables in L. There are only k over epsilon square variables. That restriction takes time 2 to the k over epsilon square, going over all possibilities. And for each I in k, you have one of the following. Either after the restriction, the sign of pi has become close to a constant, so then just pretend it's a constant, replace it. It's trivial now. Or lambda max of pi is small compared to its variance, and you can apply the CLT. And clearly all this can be done in time, poly n times some function of k and epsilon. So this was the toy case. What happens if all of them are not diagonalizable in the same basis? So then you can't do this orthogonal transformation in the very beginning, because there is no basis in which all of them look diagonal, all the polynomials look diagonal. But you can try to do it one by one. So, and the key concept again we are going to use here is that linear forms of Gaussians are Gaussians. So basically if you have, suppose you are given a function f of x1 to xn, where x1 to xn are drawn from a standard n-dimensional normal. Given any linear form L1x whose 2 norm is 1, so if you are given a linear form whose 2 norm is 1, consider an orthonormal completion of this basis L1 to Ln. then f of x1 to xn can be re-expressed as g of L1 to Ln, where the certain properties, like if f was a quadratic polynomial, g will continue to be a quadratic polynomial. So you can now start making, given any linear form, you can rewrite f in a basis where you make L1 as one of the variables. And so it makes sense to restrict on all possible values of L1. So this is the key observation we are using. And so again we'll start doing the same way. So we'll say either the conditions of the CLT are met, that is eigenvalues are small, and then you can just apply the CLT. If not, there is a linear form, otherwise just assume that lambda max of P1 is big. Just assume that lambda max of P1 is big. You can do so without loss of generality. And then there's a linear form L1 such that if you express P1 in the basis of L1 and some orthonormal extension of L1, then P1 can be written as alpha 1 L1x square plus beta 1 L1x times R1 plus Q1. R1 here is linear, Q1 is quadratic, and R1 doesn't involve the linear form L1, and neither does Q1. And in fact, R1 and Q1 are independent of L1 because they are only involving the variables L2 to Ln, which are orthogonal to L1. And furthermore, the variance of Q1 is at most 1 minus epsilon. So in particular, you can consider restricting on all possible values of L1. This is not exactly possible because L1 has a Gaussian distribution. It's not a finite support, so you can't go over all restrictions, but you can discretize and do something. Yeah. So you substitute. So you just consider what happens when L1 is this value, so you can't go over the infinite support, but discretize and go over all possible values. And what happens now is, so you can continue doing this recursively. I'm being very hazy here, but this the main idea goes through very easily. That we can continue recursively until all the Qi satisfy one of the two possibilities. Either after the restriction, lambda max of Qi, so the variance of Qi is substantially large compared to its maximum eigenvalue, or the variance of Qi has become very small. If the variance of Qi has become very small after all the restrictions, remove it. And then you have essentially gotten something very similar to a junta, not really a junta, but a junta plus linear form. And if not, in the first case, you have a condition to apply the CLT. Basically, this can go on for at most k over epsilon square steps. The reason being that at every stage, you at least take epsilon fraction of the variance of at least one of the guys. There are only k guys, so total, you can go on for at most k over epsilon square steps. Being hazy here, but basically it means that after all this, after going over k over epsilon square steps, where you can algorithmically do this restriction, you'll be in a case where you can apply a mix of the CLT or brute force and do the thing. It's not hard. It's a bit tedious, but it's not hard. Okay, so that leaves me with the CLT. So I still have 10 minutes or 15 minutes. That's good. Okay, so now the main central, let's recap what's the central limit theorem we are trying to prove here. So all that is left is we are trying to prove a central limit theorem now. Let P1 to Pk be quadratic polynomials with whose variance is bounded by 1, maximum eigenvalues are bounded by epsilon, and at least one of them has a variance lower bounded by C. Then the joint distribution goes to a normal in Kolmogorov distance, with this being the bound on the Kolmogorov distance. Okay, how do you prove this? So there are two keywords here. One is Stein's method and the second keyword is Malliavin calculus. I'm going to go over the first one and the second one. So first let me go over Stein's method. So Stein's method is inspired by this very easy to prove but important fact that if you have an absolutely continuous f and whose f bounded derivative is always bounded, and if z denotes the standard normal, then
If the derivative is also always bounded, does it mean already that it's absolutely continuous?
My analysis is really bad, so maybe it implies directly. Okay, if z is a so let me refer to them as nice functions. So if f is a nice function and z is a standard normal, then the following identity holds good. Expectation of z times fz equals expectation of f prime z. This is a very simple fact, and how do you prove it? just integration by parts. Just write the expressions of z times fz and f prime z. Integrate, you will see that thing. It's a very simple proof. Turns out that the converse is also true. So if for a random variable z it holds that for every absolutely continuous f with a bounded f prime, this identity holds good, then z is the standard normal. How do you prove this part? So it's some basic differential equations, not very difficult, some amount of calculus, not very difficult. But turns out this means that this equation is a characteristic of, it characterizes standard normals, exactly. And so the next question to ask is this characterization robust? That means, can we say make a meta statement like this, that if expectation of zfz minus expectation of f prime z is always small for a very large class of functions, then z is close to a normal in some metric. Can we make this kind of thing? And turns out this is the basis behind Stein's method. So an example of a theorem from Stein's method is the following lemma, that if you are given a random variable w such that expectation of f prime w minus wfw is always bounded by epsilon, its absolute value is bounded by epsilon, where f can be chosen to be any function whose infinity norm is also bounded and the derivative's infinity norm is also bounded, then the total variation distance between w and the standard normal is bounded by epsilon. You can say, okay, what about if I try to prove something like a weaker distance metric, like the Wasserstein distance? Well, then you have to prove the smallness of this quantity for an even smaller class of functions. So you can restrict yourself to a class of functions whose whose not just the function is bounded, but its first and second derivatives are also bounded. Okay. So I'm just giving prototype of theorems that can be proven using Stein's method. Okay. So what are we? So remember, we are trying to prove convergence to a multivariate normal. It's not a single normal we are trying to prove closeness to. There are similar characterizing equations for multivariate normal. Unfortunately, I'll not go into it because it take a lot of effort. So I'm not going to go into how to prove closeness to multivariate normals, but it's basically the same kind of characterizing operators. You have to bound certain numbers, certain things. So I just focus on the univariate case of Stein's method and how Stein's method is used in this context, in context of polynomials of Gaussians.
But like in the multidimensional case into your hypotheses, it's not necessarily the case that you converge to a normal and say,
no, we won't. We won't converge from a normal in the Earth mover metric, but we'll converge to a. So Earth mover metric is characterized by test functions, so the first derivative is bounded. You can show that the convergence is in respect to test functions whose second derivative is bounded, but second derivative is good enough for us because we just want Kolmogorov distance. Earth mover metric is stronger than Kolmogorov distance, right? So, okay. So how will we apply Stein by the principle of conservation of difficulty? So we are now trying to prove that some polynomial. So consider the basic case that you're trying to prove some polynomial of Gaussians is close to a normal. You apply Stein's method. So now basically you have to prove that for every function, if w denotes a polynomial of Gaussians, then for every function f, say from this class, f prime w minus wfw is bounded. And you have just transferred the difficulty to this kind of a problem. How do you analyze this expectation? How do you prove this expectation is bounded? And this is, so just for the moment, don't think about Wasserstein or total variation, just how do you bound these kind of quantities? And this is where the next keyword enters. So our variables here, random variables of the form polynomials of Gaussians. And this is where the next keyword enters, Malliavin calculus. In a nutshell, Malliavin calculus allows us to take derivatives of stochastic processes. I'm afraid to say anything more than this because I'm afraid I'll say something wrong. But this is informally what it is. And the derivative in Malliavin calculus is basically somehow taking derivative with respect to the chance parameter omega. So if omega is the sample space, capital omega is the sample space, you're basically taking derivative with respect to elements of the sample space. We don't require all these interpretations. I'm going to define this syntactically in the next slide, and you're going to see it's very simple. So all the complexity comes from infinite dimensional Gaussian processes. We are sticking to dimension n. So here is the definition of the Malliavin derivative. Let f be a function on R to the n, real valued function, and the domain is equipped with the standard normal measure. Assume f is a nice function, so you require certain smoothness conditions. So basically you require something like the derivatives have polynomially bounded growth. For us it's polynomial, so everything has polynomially bounded growth. Then the Malliavin derivative operator D maps f to a R to the n valued random variable whose ith component is just the partial of f with respect to xi. The reason this definition becomes complicated is when you are dealing with infinite dimensional Brownian, infinite dimensional domains, then you can no longer write d of fi equals del f over partial. Sorry.
What is the random variable? I mean,
So consider the function being just x1 square plus x2 square plus xn square. Then the first component is just 2x1. So x1 itself is a random variable, right? So this remains now R to the n valued random variable. Okay. The main, I think, technical issues come when you take like Brownian motions. You're considering functions of Brownian motion. That is when these things become really complicated and used. But for us, the thing is very finite dimensional and everything is very nice. So you can in particular write dfi equals del f over del xi. Otherwise, you can't write that. There's a basis independent definition of this thing. So it's a calculus. So there are lots of nice things that hold good. In particular, so I'm just giving my example. It's a calculus. Lots of nice properties, lots of nice things hold good. For example, let h be a vector in R to the n. So just be an element on R to the n. And wh denote the Gaussian random variable in the direction of h. So it's just summation hi xi. Then you can very easily prove that expectation of f times w of h, f is some random variable in this Gaussian space, equals the expectation of the inner product of df with h. Note that df is a random variable, so it makes sense to take inner expectations. And this is the analog of integration by parts in this calculus. Lots of nice identities hold good. That's what I'm trying to say. I'm not going to use it anywhere. I'm almost okay. I still have some time. Okay, so why am I talking about Malliavin calculus? So this is the reason I'm talking about Malliavin calculus. So this was first in a paper by Nualat and Peccarty from 2004. And it's a very simple identity that if w is a random variable in the space of in this functions of Gaussians, it's a function of Gaussians and it's nice enough, again, polynomially bounded derivatives and all that, then the following identity holds good. Expectation of f prime w minus wfw equals expectation of f prime w times this quantity 1 minus inner product of dw and minus dl inverse w. Okay, I have explained what the operator d does. It just takes derivative with respect to these xi's. I need to explain what the operator L inverse does, and it's very simple. Assume the function has a Hermite expansion. Just attenuate the qth level of the Hermite expansion by minus 1 over q. That's all it does. So, and you're not going to do anything with the level 0. So you're not, the 0 part will be taken out, it will vanish, and the qth part of the Hermite expansion will be attenuated by minus 1 over q. And this identity holds good. Again, it's an identity. If you know the right calculus identities in this thing, it's not a very hard statement to prove.
Can you just prove it? I mean, these expressions are easy to express with the Hermite expansion, right? I mean, this d was just a gradient, right? And
yeah.
So can you just write the Hermite expansion of everything and
I think
it'll pop out?
I think so. Yes. Yeah. I mean, it ought to, and I think it will pop out very easily.
Okay.
Yeah. And it's an identity, so not too much. It can go only one way from left to right. Yeah, I think it will pop out very easily. Again, most of the complexity comes when you have infinite dimensional things. So maybe there's an easier way of doing all this rather than using this hammer. Okay, but this looks useful, right? So on the left hand side is the term we wanted to bound in Stein's method. And this is saying it's exactly equal to this term. There's still a f prime w popping around, which we'll get rid of it in the next slide. So it's equivalent to bounding the right hand side. We now just want to bound the right hand side. Okay, so the first equation is just what I wrote earlier. Again, you can show the following thing. If the variance of w is 1 and the mean of w is 0, you can show the mean of this quantity is equal to 1. Again, not difficult to show. Maybe just doing the Hermite thing will show this thing. And hence, now next observe that since f is a kind of function that is coming from Stein's method, where always the first derivative was bounded. Hence, by Cauchy-Schwarz here, it suffices to bound the variance of this random variable. So this is tremendously important. Now we have reduced this closeness to normal to just bounding the variance of a random variable. But W is this explicit thing we are trying to prove close to normal. Just take this dW, dL inverse W, work it out syntactically, and we are just trying to prove the variance is bounded. This is something much simpler, potentially much simpler. So that's all it boils down to. So it all boils down to controlling the variance of this quantity. So this is how Stein's method and Malliavin calculus interact with each other. For us, okay, so am I supposed to stop at 2:30 because I'm really close to 2:30? Okay, so I'll finish it as quickly as possible. So we are trying to prove closeness to multivariate normals. So far I was just talking about univariate normals. So the characterizing operators become slightly more complicated to write on the board. I'm not going to do that. But here is an example of a true theorem which is already was known to be true in literature. That if you consider the class of functions on R to the k to R, whose from R to the k to R, whose second derivative is bounded, and let Z1 to Zk be a Gaussian distribution with the same mean and covariance as W1 to Wk, then Nordin and Peccardi showed that W1 to Wk and Z1 to Zk are close to each other with respect to the class of test functions H, with something bounded by k square epsilon, as long as you can show that the variance of this quantity dwi minus dl inverse wj is always bounded by epsilon for any choice of I and j. This is like when it was one dimensional, then you had dwi, now you will say all possible i's and j's from 1 to k. If all of the variances can be bounded, then you can show this. Okay, so what will we do? Well, we want to prove this theorem. So first we wanted to show, so we just show this theorem that if wi is a quadratic polynomial whose variance is 1 and lambda max is bounded by epsilon. Okay, so all wi's and wj's. Then we show that this quantity is bounded by epsilon. And how do you prove this? Just calculation and a little bit of matrix analysis. Not difficult, just a page or so. And that proves that if we have been given a collection of degree 2 polynomials whose eigenvalues are bounded, then it's close to a multivariate normal with respect to this class of test functions H, meaning the class of test functions which have a second bounded second derivative. Who want to get closeness and Kolmogorov distance? Not a hard job from here, right? I mean, what will you do? You will take the interval functions, smoothen it out, standard stuff. Nothing very no rocket science going on. This is what we do, but yeah, I guess everybody knows what is to be done. Okay, so recap: we have the central limit theorem, and if you have the so CLT allows us to, so in the recap, CLT allows us to do approximate counting as long as all the eigenvalues are really tiny. If some of the eigenvalues are large, we can apply this decomposition to reduce it to a combination of CLT plus brute force, and you can use the regularity lemma to move from the normal to the Boolean hypercube. Thanks.
More questions?
This is also this fourth moment stuff, right? Where if you show that if the polynomial has the fourth moment that's like 3 or whatever, then I see.
Exactly. So this is also
there a
the
multi-dimensional version of that fourth moment stuff?
What's that?
Is there like a multi-dimensional version of that?
I don't think so. I don't know. I don't know. Maybe there is. I mean, the fourth moment stuff says that if something is restricted to a level of the Wiener chaos, so you have to just consider something which is homogeneous.
There's a multi-dimensional version because if you have a probability distribution in several dimensions where any linear function of the output is Gaussian, then it's Gaussian.
Yeah, okay, but maybe some easier to check. I'm just wondering, like, can you like use that theorem? I guess the k=1 case was easy for you anyway, all right? But
yeah.
Could you also prove it by the fourth moment thing? I mean, not that it's maybe necessary.
The fourth moment thing, but again, the fourth moment thing, if you just want to apply that theorem as a black box, the fourth moment thing has to assume that the polynomial you're given lies completely in the Wiener chaos of degree 2. So it's a completely Hermite degree 2 thing. We have Hermite degree 2 plus degree 1 thing.
Is there a big moral difference though between?
I don't think the degree 1 shouldn't morally add to the complexity. It's an easier thing. We know how to handle what's the Gaussian. We know exactly what the Gaussian is. I just don't know how to apply the theorem as a black box. But I think everything.
But is this how they prove that theorem, or it's more complicated?
No, I think this is how they prove that theorem. I think like most of the bulk is actually getting that identity. Once you get that identity from there, like it's an identity. If you know that to be true, the rest of the things just follow. I don't think okay, maybe there's complexity if you're dealing with infinite dimensional things. Maybe there's complexity. Yeah.
Okay, other questions, comments? Well, in such a case, I want to remind the audience that we have an open problem session also today. So, think about open problems. It will take place at 3:40. And otherwise, we'll reconvene again at 3, and let's thank the speaker.
Sorry? No, that was good. Thank you.